Thank you so much, Harsha. Okay, so I'll kick this off with a little introduction. My name is Matt. I'm here with Tycho. I'm working at a company called Exo Labs, and Tycho was working with us over for a few months this spring. And whilst Tycho was with us, we worked on this paper called KPOP. And this paper is kind of twofold. There are two halves to it almost. Can you go to the next one?
Yep.
Yeah, so this is kind of twofold, this paper almost. We introduce a new optimizer and we talk about training ML models on Apple Silicon. These might seem kind of unrelated, but I hope that we'll explain why this is relevant throughout the talk. So as a bit of background on who Exo are, who we are as a company, we started as a project for aggregating spare compute. We were trying to solve the problem of inaccessibility of compute for machine learning jobs. Chips are expensive. They're expensive to rent as well as to buy. They're kind of hard to come by if you want to buy the top chips. And we wanted to be able to do machine learning stuff on any hardware. So we've got this open source repo that you can see a screenshot of in the middle there that lets you run this daemon on a bunch of devices, and they will auto discover each other. They will connect up, and they will be able to run pipeline parallel models between them. So you can take a really big model, for example, this is a stack of 4 Mac minis. If they're 16 gigabytes each, then you've got 64 gigabytes total of memory. And so you can run up to a 64 gigabyte model on these devices, kind of split across the devices, something you wouldn't be able to do usually if you didn't have that much memory. There's some strong motivation for this. This lets you run the models on your own devices, which is great for privacy. You might be concerned about sending things to an API. You might be a company who has confidential data. The fact that we can run full-size cutting-edge models on-premise, like in this box, is fantastic. Like, you can have them completely air-gapped. You might be able to say to a company that has private data or something, literally, we will take the model on a USB stick and we'll plug it in, and we'll put the model on the device, and the device never has to be connected to the outside internet. There's the other question of why Macs? Why do I have a bunch of photos of Macs here? We have done things with lots of consumer-grade hardware. We've done things with consumer-grade NVIDIA and AMD chips, but it turns out that the Macs are really, really good if you're wanting to do single request inference. So if you're just chatting with the model, what you care about is your latency. How many tokens per second can you output? And the Macs, because they have such a high memory bandwidth, they can read the model fastest. And if you're doing single request inference, what you care about is how fast can you read through the model. Because you want to be able to generate as many tokens per second so that it's like at human reading speed.
So are you saying that Macs perform better than, say, some NVIDIA machines in single inference?
Yeah, in single token inference, yes. And there's also the question of like how fast can they transfer the tensors around between the devices. But there's a bunch of different dimensions, and I guess the main dimension with respect to running big models is that if you wanted to run it on a bunch of 4090s, a big model on a bunch of 4090s, that would cost a lot of money to buy the 4090s that had sufficient memory to be able to do that. So we go with like completely just consumer grade, like these Apple devices are all like just the same, and they turn out to be really good for single token, single request inference, just if you're chatting. That being said, yeah, like if you're doing something batched, if you have 1,000 documents that you want to summarize, the NVIDIA chips, because the NVIDIA chips are so much faster, can compute so much more, they have much higher flops, the NVIDIA chips will be much, much better for that sort of thing.
Okay, awesome.
So the idea is that we've got a bunch of these Mac clusters that people are going to be running that are doing these inference things. people might be doing inference on them sometimes, but they might have them kind of idle sometimes. So if they're idle, then maybe we can offer for them to be able to train on these clusters as well as just doing inference. So that's where this paper comes in. Can you switch to the next slide, Tycho? It seems kind of crazy if you say to people, oh, we want to do a training run on Max. We want to train a model on a bunch of Macs, or maybe fine-tune a model on a bunch of Macs. People are skeptical that this is even possible. NVIDIA's specialized hardware is purpose designed to do AI workloads, and it's really good at doing AI workloads, whereas Macs are these generalized consumer-grade chips. But this is where the idea of the hardware lottery comes in, which was this paper by Sarah Hooker from Google Research. Can you go to the next slide? The idea of the hardware lottery is that the algorithmic advances that we come up with in machine learning are kind of directed by the hardware that is available. What we think might be the cutting edge, the global cutting edge, actually ends up being kind of the cutting edge conditional on what the best hardware at the time was. So almost Adam, for example, or transformers and NVIDIA were kind of co-developed. They kind of developed symbiotically. And so as a result, the algorithms that we build are super optimized for the sort of hardware that we have. So if we think of the thought experiment of a world in which the hardware profile of the cutting edge was super different to that of NVIDIA, say you had a lot more memory or a lot less flops, would Adam, the optimizer, still be like the de facto trading algorithm? Maybe it would be something different. So this is kind of what motivated the idea of maybe we can, if we're training on Apple Silicon, obviously if we just do the same algorithms as we always would on NVIDIA, then it's probably not going to be as performant. But if we make some modifications that make the optimizer more suitable to the hardware profile that we've got, then maybe we can start making some progress towards making Apple Silicon training feasible. And with that, I will hand on to Tycho to talk about what we did with the optimizer.
Yeah, thanks, Matt. As mentioned, I worked on this project with Exo earlier this spring, and what we looked at is we developed this new deep learning optimizer called KPOP, one of the reasons behind looking into KPOP or different optimizers was that we sort of settled on this Adam optimizer for many years in the deep learning community. But maybe if you have more memory or if your hardware specifications are different, then maybe other configurations may be more optimal. And one of the things that KPOP does is it gives you more flexibility to sort of tune the footprint of your optimizer. But then other than that, it's also a great optimizer. So it's sort of interesting that even on sort of a typical NVIDIA workload, as we'll see, it's very competitive compared to other state-of-the-art methods. More on that later. Let's talk about optimizers first. Oh, yeah, and then this work was presented in this paper, which was accepted at the Efficient Systems for Foundation Model workshop at the last ICML. Okay, so optimizers. What do we mean when we say a deep learning optimizer? Well, with these huge neural networks or LLMs, we have a very high dimensional parameter space. So this is a point with many dimensions, and we have this loss function or objective function, like predict the next token, and we try to minimize this loss. And one way to do this is simple, and we can take gradients of the loss. So one way to do it would be to take sort of steps in the direction that point downhill. So this is a classic gradient descent, or if you do it on mini batches, you get an unbiased estimate of that gradient, and you take steps in that direction. And this works, but you need to tune the learning rate really well. So if you if steps are too small, convergence is slow, and if steps are if your learning rate is too high, this happens. So you often overshoot. So you will reach like somewhat closer. You get somewhat closer to the goal, but you're taking a lot of steps again. So one way to counter this is by adding some momentum or damping. So this is like SGD plus momentum does better. It removes some of these oscillations by smoothing the trajectory. But still, you have this problem somewhat, and you also need to really tune this new hyperparameter, and it can be somewhat difficult. And then there's this more sophisticated approach called taking the natural gradient, where you take the or their methods based on Hessian, or in this case like the feature information matrix, where you intuitively you sort of use the underlying curvature, and then you know that in directions where the loss landscape is going to be flat, so you could measure this sort of locally. Then you can take larger steps in those directions. But if the curvature, so the second order curvature, not just the gradient, is steep, then maybe you need to be you take some more. So that's the intuition behind it. Now in practice we use Adam. So what is Adam then? I think it's sort of, I see it as somewhat in between. So it has these. If you look at the pseudocode, I know it's not good to put a lot of text on a slide, so I'll try to guide you. But yeah, you maintain an exponentially running average of the average gradient and of the square of the gradient, so the first and the second roll moment. And then when you take a step, you're saying, so this is the line at the bottom, you're not going to take like alpha, the learning rate, times the gradient, but you're taking the average gradient, the smoothed out gradient is m times that t, and you're also dividing it by the square root of the variance. So this is sort of this adaptive learning rate, if you will. And the square root is a bit peculiar. Yeah, I'll discuss later. I think it's a bit mysterious. I think, yeah, my interpretation is that it's sort of taking conservative, sort of being a bit more conservative than the estimate tells you. But without that square root, you could interpret Adam as doing a sort of diagonal version of a natural gradient. So it's basically preconditioning your gradient, doing natural gradients, but we're not using the full Fisher information matrix, but we're taking this diagonal approximation. And we also have sort of a momentum where we take the average gradient. So yeah, one interpretation would be that it's sort of diagonal natural gradient with a twist. Now, this is great. It's like this adaptive optimizer, and it works really well. But what it cannot do, it fails to capture correlations, basically. So what does this mean? It's basically if two weights, for instance, have variance when they are large together, but not if they are, but only simultaneously, then they're correlated. And in terms of curvature, you could imagine that sort of if you take a gradient step in the direction of both weights, then you should take a larger step. But if the gradient only points in one direction, then you maybe not want to take a large step. So this is the kind of thing that Adam cannot capture. So it is diagonal. It still works surprisingly well in practice, but yeah, it's sort of one thing to note, but it also makes it very efficient. So why don't we use this? Why don't we use the full natural gradient? Well, the answer is simple. It's not practical at all. So this is yeah, one of my favorite slides that you can reuse for in many projects, where if you think of a 30 billion model parameter like large language model, then the Fisher information matrix would sort of explode because you square it grows quadratically with the number of parameters. And to make it explicit for this language model, it's like 170 exabytes. So exabyte comes after like gigabyte, terabyte, petabyte, and then exabyte. So you can imagine this is not something you want to compute every iteration of your optimizer. Like this is your optimizer state that blows up. Is that a question? No. So one, a diagonal approximation is very crude, but an alternative to doing a diagonal approximation would be to use KFAC. So KFAC, it's already 10 years old now. So introduced by Martens and Gross. And the idea is to say, okay, we're going to assume that layers themselves are independent. So this gets rid of all the correlations between layers. But then still, you get a sort of block diagonal curvature. But then still, for each weight matrix, it's still too costly, because if it's like a 500 to 500 weight matrix, like input-output dimensions, then the total number is like 250,000, I think. And then the square of that is going to be sort of the number of parameters in your Hessian. So this means that you sort of still need gigabytes to store the Hessian. Whereas if we do this independence between inputs and outputs of your, so you could interpret this as like a Kronecker-factored approximation, then it scales quadratically in the input and in the output separately. So this means that you sort of get a Hessian for the input, which is like 500 squared, so 250,000, and also an Hessian for the output, but they're like megabytes, because 250,000 is like nothing. So this is the reason why it scales, and it's very practical. And there are examples in literature where this KFAC approximation has been scaled to like billion of parameter models. So that's great. And then there's this very interesting extension of KFAC where you say we're not gonna use the eigenvalues of KFAC, but we're gonna sort of take the SVD of KFAC. We're gonna look at the eigenspace of KFAC, and then you can interpret it as sort of, it diagonalizes the parameter space. And what they do in this, so George et al. 2018, so the KFAC paper, eigenvalue corrected KFAC, they do SGD steps in this rotated space. So you rotate the parameter space using the Kronecker, sort of using the eigenvectors of the KFAC approximation. And then you're in this new sort of rotated parameter space called the KFE, Kronecker-factored eigenspace. And that space is very diagonal. So there you can then take like a simple SGD step. Now, when we thought, why, if this, and this is very, you sort of left and right multiply. So these are efficient transformations once you have these matrices or preconditioners. Why use SGD in this KFE space? Why not use Adam? So we have Adam, which is like great adaptive optimizer that assumes diagonal curvature. Actually, maybe that's a great fit for this diagonalized space. So in Adam, you do sort of Adam steps, but you're in parameter space, which is sort of correlated. And then in KFAC, you take SGD steps, so you correct the eigenvalues of KFAC, which is doing SGD in this KFE space. And what we do is we say, okay, we do Adam in the KFE. And funnily enough, this actually in the conclusion of KFAC, this was also mentioned as an idea. So it's not that original. They said like one could apply adaptive algorithms like grad, prop, or Adam in the KFE, but this is left for future work. And I do now know of some tries, so that this has been attempted. But I think the problem with just doing this, that you get this explicit preconditioner that is very costly. So I do think it's a great idea. It's just when you just do this, then it's not a practical optimizer, because you're doing this costly preconditioner too often. So in wall clock time, it's just going to be too slow. And I think that's why maybe these tries didn't get the traction that they may have deserved. So what we do to overcome this is we say we're going to schedule the preconditioning. So we're not going to compute this rotation matrix to go to the KFE every iteration, but yeah, we get the statistics, and then maybe every 100 or 10 iterations, we're going to update this rotation that diagonalizes parameter space, and then we're going to do fast Adam steps within that space, and then yeah, and then we're gonna like just occasionally update, and then we're also using this QR. So this is very similar to SOAP for those who are familiar with like optimization literature. And in a way, you could think of KPOP as sort of being what SOAP is to shampoo, KPOP is to KFAC. And yeah, but maybe there are some slight differences in the way we schedule. So we schedule with a warm-up. We do a lot of iterations in the beginning because then the curvature changes. And then once it's settled, we just have like a frequency. So there are two hyperparameters. And yeah, I'll skip this slide because it's too many details. But the basic, or yeah, let's go over the sort of the statements in italic. So we compute the gradients. Then we maintain sort of the exponentially moving averages needed for KFAC. And then if the schedule says you need to update, then you compute like the eigenbasis, or you do that. This can be done in like a fast QR update to also reuse the previous estimate. And then the update itself, it's basically you rotate, which is like a left and right matrix multiply. Then you do simply Adam. And then you rotate back to the original space. Yeah, and then there's one version we call TopKPOP, where we say, okay, we're not gonna use the all eigenvectors, but we're using only the top eigenvectors or a subset of the eigenvectors. And what you then get is, yeah, you can think of it as sort of doing a PCA, but yeah, PCA measures sort of squared error locally. And this is a PCA, it's sort of KFAC. So it's a principal KFAC eigenbasis, or you can think of it as sort of yeah, using the principal component of your final perplexity loss, but then yeah, with these sort of linearized or like approximate assumptions. And this is pretty cool because everything happens in the new TopKFE. So we project, and then everything becomes very cheap because all gradient communication in like distributed training, and we only need to communicate these yeah like projected gradients, or the optimizer state becomes smaller because Adam operates in this lower dimensional space, projected space. Yeah, and then yeah, and all the computation happens in this smaller dimension. So you get like the gains sort of are almost everywhere. And you do pay in performance because the quality of your grades goes down. But to come back in our initial motivation, we think this is interesting because it sort of offers you a knob to change the footprint of your optimizer. So this is that's why it may be relevant for if your maybe your hardware works very well at 0.7%. And the other way to make it very efficient is that we have a distributed version. So maybe you sync the parameters and the steps, but there are also a lot of things that you can sync. Maybe the KFAC statistics, you only sync just before you do this QR update, and which still offers an unbiased. Yeah, okay. I'm not going to make too many times, but the more importantly, the local, a lot of things stay sharded. So the preconditioners are actually sharded. GPU1 only computes the preconditioners of sort of one over the number of GPUs of the model, and maintains an optimizer state over that. And yeah, that's how a lot of savings can be achieved. Yeah, so I think this is sort of very promising direction. There are still always some open questions, so I like to be sort of open about the open questions. I still have personally, so there may be people who have answers or partial answers to these questions, and I hope they can share any insights with me if they want. So one question I have is still sort of the square root. There are many interpretations why it's needed. I think like in Adam, even in the KFE, we found the square root to be needed. And yeah, I think sometimes you hear this is needed because it brings it on the same scale again, like it's a squared gradient, so you squared once, then you need to take the square root. But yeah, I don't find this as satisfying. I would love to have a deeper understanding. And yeah, my current way of thinking of it is that we do all these approximations, and it's also based on sort of this local Taylor expansion. And maybe, yeah, you are just a bit more conservative, so there's some intuition behind it. But yeah, still, why square root? And also, yeah, maybe there's sort of a deeper reason, which would be interesting. And then I think one of the best state-of-the-art optimizers at the moment is Muon. I'll discuss a bit how this relates to Muon in the next slide. But there have been sort of I think there's this deriving Muon blog post by Bernstein 2025, where they derive Muon through this sort of spectral norm. So yeah, I do like our sort of KFAC because it provides this story from a natural gradient perspective. And I'm just curious if the two are related in some way, and if there's this yeah, sometimes there's like different families of optimizers and they all have their own story, but it would be great if there's sort of a unified perspective that covers all optimizers instead of yeah, having sort of hearing always the same story to motivate a single optimizer. Yeah, and I know that there are people that are way smarter than me that have thought deeply about it, and there are not that many references on these slides. So yeah, I hope people won't be offended, but yeah, I'll move on.
Did you say there are people way smarter than you?
Yeah, I think so. Yes, that's a statement I can be confident about.
I could barely understand what you were saying here, so you must be smarter than me at least.
But yeah, that's. I was hoping to get questions in between. Is there any way I can? Yeah, if it went completely over your head, maybe not. But if there are any questions, then I'm very happy to answer them at this point.
Yeah, I think we just unmute and go ahead.
Go on. All right, I'll go on. Okay, so I'm almost done with the K-pop. Oh, do I see a hand?
Yeah, I was just saying that they could unmute. Paul, do you have a question? Okay, it was by mistake.
Yeah, no, I'll wait a little bit before I ask the question.
Okay. Yeah, so this slide is almost done. So basically, we evaluated this optimizer on the NanoGPT speedrun. So this is a very competitive benchmark on where they by Keller Jordan, where they have like 8 H100 GPUs, and they used like this NanoGPT by Karpathy repo and tried to really optimize it. And I think the current record uses this Muon optimizer, and it's just below 3 minutes. And the goal is to achieve this perplexity loss of 3.28 without with some rules. Yeah, and yeah, so on this speedrun benchmark, we do outperform Adam by a large margin, and we are on par, but we're still slightly below the performance of Muon. But I think this is still very noteworthy. One, because sort of Muon needs to orthogonalize every iteration. We have this scheduling we can do. Then the question is like, why is Muon still faster? Because they do this very smart Newton-Schultz iteration every, which is so fast that even though they need to orthogonalize every step, they're still ahead. But maybe it's sort of I still think that KPOP is a very nice sort of alternative approach that, yeah, maybe if things are smarter or faster, like there's no QR decomposition in bfloat 16 in PyTorch, maybe with some of these advancements, it could actually outperform Muon. So yeah, I would be very interested to see if that's actually true. And also this benchmark has been largely optimized in conjunction with Muon. So you could argue, okay, maybe because Muon, I think like 90% of all commits or records used Muon. Maybe other optimizations are sort of chosen that work really well with Muon, but yeah, maybe we need to optimize more of the code base to really see how well KPOP performs. But yeah, it's very close. It's like 0.04 in perplexity, and it uses and this was in 2.84 minutes, and then we did try to like a few more steps, but then yeah, we didn't. We were often stuck around 3.32, I believe, around like that minutes. But yeah, I still think it's a great result. We can be very proud of it. Yeah, so this is where my part of the talk will end. So if there and then Matt is going to talk a bit more about experiments we did on Apple Silicon. So if there are any questions related to the algorithm itself, to this KPOP optimizer, yeah, maybe I went through the slides a bit too fast. So then please ask them now, and then I'll try to explain.
I think you're muted.
Yeah, sorry, my question was, is this a algorithm you're publishing open for people to adopt, or are you gonna bundling it as a product?
Right. So we did describe this algorithm in the ICML paper. So it is there in that sense. It's all open information. Yeah, and then as regards to again, I'm not with Exo anymore, so I cannot really make statements about their current plans. I do believe that at some point this code will be made public, but maybe Matt can comment on that.
Yeah, we're going to open source the. Have we not open sourced the repo for this yet, Tycho?
No, I don't think it's open.
Okay, we're going to put this. So this paper was released like a month ago, something like that. It's open research. Yes, we might end up using it in our own product, but it was like done as research for the academic community, and if other people find it useful, then they can use it. We might end up also using it in our products. But yeah, the code will be open source soon.
Okay, that's good.
Hello. Hi, Tycho and Matt. Thanks for your talk, and also I agree with you that you are too fast in your algorithm. So basically, there's a slide, the why not to Adam, but in the KFE, and there are 3 diagrams. Could you go back to that slide? Yeah.
This one.
Yeah. So could you explain more about this diagram? It looks very fascinating, but I'm not quite sure about its meaning.
Right. Yeah. So basically, the dot. Do you see my mouse, my cursor?
Yeah.
Yeah, I think so. Okay, so basically, this is like a 2D visualization of the very high dimensional parameter space. So this point is like our current parameters, and then in Adam, it sort of hides all the clever things Adam does, but you get a gradient, and then you do an Adam step, and this is basically the Adam step. So if you do like one iteration using Adam, it will bring you from one point in parameter space to another point in parameters. So this is sort of the change. But I'm putting it in red because I think that sort of in the parameter space, the assumptions of Adam are not that great. So Adam assumes that the curvature is diagonal, that weights are more or less independent. If one gradient direction and another gradient direction together are moved, then so it's sort of it's hard to explain maybe without a whiteboard, but I'm basically saying, so that the picture is saying that if you do Adam directly in parameter space, it may work, but it's not the best thing you can do. And then what KFAC does is it changes the parameters. So it's basically saying, okay, before we do the update, we're gonna multiply it with these matrices. Now you get a new vector, and then we're doing an SGD step, and then we're multiplying the resulting vector again, or we're transforming it again, and then we get back to a point in parameter space. So this is like what each KFAC does. You can see this sort of an algorithm. But then part of that algorithm that moves you from here to here, you do along the way, you do this SGD step, and we say no, here you want to do Adam. That's basically you have a point in parameter space, you perform this transformation, and then you have a new point in parameter space, or in practice you transform the gradient because of linearity you can do this, but you get your standard gradient, you transform it, then you act like as if nothing happened. So you do all the steps that the algorithm and the Adam algorithm does, and before applying it to your parameters, you rotate it back. You do this transpose, you multiply it with this matrix, and then we say that doing these steps, adding these sort of preconditioning, so adding this transformation before and after Adam, that is much better. And then we show that in practice in our experiments, we get an algorithm that is like converges better. You get a lower loss faster than Adam.
Okay, thank you. So basically, there are so how many loops here? I guess there are nested loop, right? When you are doing KPOP, you are actually doing the Adam. In the KFE space, you are actually doing the operations on the Adam. So I guess there are only two. There are only two loops, but maybe equivalent to 3 loops or something like that. I'm not quite sure about that.
What do you mean with loops?
The iterations. When you optimizing the parameter space, are equivalent to optimize something in the KFE space, I guess.
Wait, maybe one more time. With loops.
Okay, I will go back to the paper and try.
No, that's fine. It's probably me. I'm also so I think you can interpret it as you'll end up with sort of taking much better steps. So you may need fewer of them. And maybe it's probably me. So please, maybe we can offline. I can.
Sure. Thank you so much. Thank you.
Right. Any other questions? Otherwise, I'll move on to.
I had a brief question. I think one cool thing I already feel I have a problem with Muon is that I now have to set parameters for 2 different optimizers because of the way it's there. But I think that's pretty cool. But the second thing is, how much more sensitive is this to, say, any kind of quantization or compression taking place on the gradient? So would you, was there analysis in that regard? And say if I were to quantize, I know the QR step potentially has to be done at higher precision, but I think people have shown that you could do Muon with FP8, for example. So I was just curious on that part.
That's super interesting. So first of all, we didn't at all explore this. So I really have very little to comment on this. There's sort of I guess there's one bit where indeed, like in Muon, the orthogonalization steps are sort of matrix multiplications themselves, so they can be done in B-flat16. They're very efficient. This is, I think, the reason that Muon is so good. It's probably not a secret, but it's like this is such a clever way of very fast orthogonalizing with just doing some matrix iterations. Whereas the SOAP and it needs to do, currently it relies on sort of QR. I don't think there are many. There's no way really to I don't know yet of something that uses something like a Newton-Schultz to replace this QR step that could maybe like run in BFAT16. But this would be super exciting future work. Like if you can, there are a few of these points where KPOP is still I think also for SOAP, this QR is a bit of a pain. It's costly, and if you could speed that up, then I think they're huge potential savings.
Yeah, thanks. I was curious because I think for the longest time for Adam, it was the second moment which was a pain for mixed precision training. So I was curious. But yeah, thanks for that.
Yeah, about that. Yeah, like all these things like quantized training or anything like we didn't at all explore that. So I would be very curious, but no idea.
Yeah, thanks.
All right. If there are no more questions, I'll move to Matt. Matt, did you want to switch?
Yeah, so I'll try to switch over.
Yeah, that's it.
Okay, please excuse this, everyone. Can people see this okay?
Yep.
Can people see this slideshow that I've started?
Yes, I can confirm it.
Yeah,
Maybe
okay,
someone can.
I can't see anyone, but that's fine. We'll deal with it. Okay, sweet. So hopefully we all have somewhat of an idea of what KPOP is doing now. And I guess I'll start with saying all of these experiments, the results that Tycho showed, these are run on H100s. So we were doing our experiments in PyTorch with NVIDIA with the mind to, at the end, go, okay, let's try run this on Apple Silicon and see if we get the same speed up, see if we get the same improvement. And so this is where I came in. MLX that you can see highlighted at the top here is Apple's machine learning framework. And so it was somewhat of a challenge to fit the algorithm into MLX, but it was also an interesting problem because training on Apple Silicon is so different from training on NVIDIA. So that's what I will talk about here. There's a number of differences, of course. I've mentioned this with the hardware profile between NVIDIA chips and Apple chips. What you can see here is that the memory capacity of the Apple devices is much, much higher. Like 0.5 terabyte of VRAM is unbelievable. And of course, we have a lot to play with there if we're going to use this to store our preconditioners, because KPOP is a bit more memory costly than Adam. On the other hand, the Apple devices are have a lot less flops, have a lot lower flops, and so they can do a lot less calculations per second. And so this is something that we really need to take into account. We want to be as efficient per flop as we possibly can. And as a result, we want to be as data efficient. So this is why we have the prior that there should be a lot of value to running a second order method like KPOP, where you're a lot more data efficient on the Apple devices. There's also a big difference in the networking. With NVIDIA, you have these NVLink, inter-node NVLink connections. And on the other hand, with Apple devices, they're not GPUs in a rack. They are discrete physical computers. And these computers they look like USB ports, but they're Thunderbolt 5 ports on the side. And so you can connect these peer-to-peer with these Thunderbolt 5 ports. They provide 80 gigabits per second bidirectional, which you can see versus the nearly 2 terabytes per second of NVLink is pretty different. And again, as I said, they're peer-to-peer, which is very different to this, which is what we get with the NVIDIA chips. So what I'm trying to highlight here is that you will have, say, 4 H100s, 4 NVIDIA chips in this box, and you might have a tensor on each of the 4 devices that you want to average between the devices. This is called an all reduce. they're in this box and they're connected with an NVLink thing, and this lets them communicate all to all. But actually how we do this all reduce in reality is we just communicate in a ring, in like a logical ring. So each device, it works in the all reduce algorithm works in stages, but each device passes, at each step, passes a portion of the tensor to the next device. So they're only communicating with the previous device and the next device. So this could scale up. If you had 8 devices, for example, you would have a lot more than just 6 connections here. And all of the connections in the middle, if you imagine this drawn in a ring, all of the connections in the middle would be completely unused. Only the connections around the outside would get used. So what do we do when we're training with Max? We said before that they're peer-to-peer, that you connect them with these Thunderbolt things. So instead of connecting them all to all, you just connect them physically in this ring that you would use to all reduce. So I'll highlight again here that the difference is that NVIDIA, you kind of get it for free that they're connected all to all, but that gets wasted. You don't actually use the all to all connections. You only logically communicate in this ring. So when we're training on Max, we just connect them physically in a ring. So moving on to KPOP, we've built up all of our fundamentals. We know how it computes. We know how they communicate with each other. And so we can start building KPOP onto our Apple Silicon devices. The first thing to note is, I've said this before, KPOP is much more flop efficient than Adam. For every computation that you do, you get further, you get closer to the optimum that you're looking for in this loss landscape. This is great because we've got limited flops on our device, so we can spend them better. We also have higher memory per accelerator, which is great. We can fit these big preconditioning matrix, big, not that big, but they're more size than you would store with Adam. They will fit into your accelerator because you've got a lot more memory going spare. And finally, this ratio is really important to consider, which is network bandwidth divided by flops. So how much can you communicate versus how much can you compute? And this is much lower on Apple Silicon. So you can communicate relatively, you can communicate a lot slower on Apple Silicon than you can on NVIDIA devices. This means that if you, for example, you're doing a training run with a global batch size of 1 million, an Apple Silicon cluster doing that training run will spend a lot higher proportion of its time communicating than an NVIDIA cluster would. This means that your utilization of your devices is lower on Apple Silicon, which is not what we want to keep, given that we're so low on flops. We want to be able to make sure we're making the most of the devices and not leave them idle whilst they communicate. The great thing about KPOP is that because it's a second order method, you can push the global batch size higher before you get kind of diminishing returns of adding more data. This means that you can, like, instead of processing 1,000 examples, 1,000 prompts per optimizer step, maybe you can process 10,000. I don't think we've exactly come up with the scaling laws for what the speed up is, but for these second order methods, we can push the global batch size higher. This is great. This means that you can communicate, you can process more examples before you have to, you can do like more forwards, backwards passes before you have to do an all reduce and communicate. So you can spend more time computing and less time communicating and leaving the devices sitting idle. These are the results that we've got on the physical Apple devices. You can see these kind of crude photos of our setups here. We had 2 sets of experiments. We ran one with just two Max Studios because we only had 2 of these 512 gig Max Studios at the time. And that was with a 35 million parameter model. As like you can see that this is quite preliminary results, but we still wanted to show that it's possible on Apple Silicon, and it does give this good speed up. And then we ran another set of experiments with these 16 Mac Minis. You can see here this highlighted number that KPOP performs in training these 11,000, training over these 11,000 iterations. KPOP performs much better than Adam does. Great. That's expected. We knew that that was expected. But if the really important thing is that we can early stop, because KPOP takes much longer per iteration, or a little bit longer per iteration than Adam does. So we can do some early stopping, and we can ensure that they both only train for 34 minutes here, and we still see that we get a big performance increase using KPOP instead of using Adam. Kind of training performance per minute, if we want to measure like that, which is great. This is exactly what we wanted to show. We're getting a little bit short on time. I'll finally talk about some of the other things that we're working on with Apple Silicon training for kind of scaling up these training runs. One thing that I'm very excited about doing is multi-dimensional parallelism. These Mac Studios have 6 of those Thunderbolt ports. And if you think about connecting Macs in a ring, then each device needs to be connected to the next device and the previous device. This is great. This means that we actually can get 3 dimensions of parallelism here. So you could potentially imagine like a data parallel, a pipeline parallel, and a tensor parallel dimension. And these will be physically arranged in those like dimensions because they have to be, because you're physically connecting them peer to peer in these rings. The other thing that we're working on is pushing the limits when we get to these scaling limits. So at some point, we're going to reach the limit of scaling with these Thunderbolt rings. We think at the moment that we can get to maybe a few hundred Macs training in like multi-dimensional rings. But at some point, they're going to top out, and we're going to get to the limits of scaling these things. And so we've been working on some distributed training algorithms to be able to communicate between these with like a lower bandwidth. We released one paper recently called SPARTA that does like sparse parameter sharing. So you'll randomly subset a small number of parameters to the model, and then you'll average them between devices completely asynchronously, which is great over a very low bandwidth network connection. So the idea is that we will, in the same way that these algorithms are typically now being used for training across data centers, maybe you've got 4 data centers across the world and they can connect with each other. We might have all of these Thunderbolt pods in the same data center, but they're then connected over Ethernet, or I've put wireless here, but that's not going to be the case. It's definitely going to be Ethernet. Doing these asynchronous sharing so that these maybe 4 pods can all communicate with each other leads to further scaling. Cool, that's all I had to say. And does anyone have any questions to ask about this? I can't see anyone, so I don't know.
I can go first, maybe, if there's no other. This is actually insanely cool too, because I'm all about consumer hardware. So as soon as I saw everything Exo was doing, just a fanboy moment in that aspect. But I'm also thinking like one thing that's underemphasized, and do you agree? Like when typically you're comparing to an H100, which has a vendor who's handling all the fancy interconnect, but would it also be like a good case to say that a stack of 8 4090s would never compete with something like KPOP as well? Is that a right assessment? Because they don't have the same kind of NVLink support, right?
Would never compete with what, sorry?
With what you have, so to speak, like in terms of if we picked up consumer grade NVIDIA hardware, like if I built like a cluster of 4090s, that's going to be super far away.
Yeah, the PCIe connection is really slow between the 4090s. I love 4090s myself because I use them for simulating these distributed training algorithms. So like SPARTA, I will pretend that we have 8 devices that are all loosely connected, but it's actually 8 4090s in one box. But yeah, for data parallel training, if you try and use 4090s, they really struggle because they don't have the interconnect speed between them. But also, you then struggle, like a 4090 has 24 gigabytes of memory. So you have to have so many, if you want to train like a full-size model, you have to have so many 4090s. Yeah, it kind of gets impractical at that point, because what if you had 8 times 24? That's like, that's not even going to compare to like a single Mac Studio or like a cluster of a few in terms of the model size that you can train on these things.
Okay, Paul can go ahead, I can ask later.
Just curious, the two Apple hardware types that you chose, the Mac Minis, the M4, were those the Pro versions or the base models? I'm just curious about that difference between the 80 gigabits per second of the lower end models and the 120 gigabits on the upper end, and whether that has any meaningful impact on your profile.
Yeah, so we had 4 of the pros and 12 of the non-pros. So of course, lowest common denominator, we were restricted to the Thunderbolt 4 speeds and the 16 gigabytes of memory. As I said, it was like very preliminary results what we've done here. We've now got 32 studios in the offer, like that we're wanting to do bigger training runs on. And so hopefully when we start releasing papers on proper full size, like we'll be able to start releasing papers on full-sized training runs at some point.
Thank you.